Hi once again. We will now complete our introduction to hypothesis testing by looking into a second method to determine if H0 will be rejected, and that is with the use of p-values. Rather than creating rejection zones to assist one's decision to reject or not H0, one can actually measure the probability that rejecting H0 will result in a type 1 error based on the sample output. I remind you that a type 1 error is the error we wish to prevent. The probability or measurement of risk is called the p-value. The decision to reject H0 is taken only when the p-value is lower than what we have set as the significance level alpha. So you have to think of the p-value as the probability of making a type 1 error, which means the probability of rejecting H0 when H0 was actually true. In practice, computing the p-value is only necessary when a sample result is in contradiction with H0, to whom the benefit of the doubt is always given. The p-value is obtained by comparing a sample result with the assumed value of the parameter that was given under H0. For example, if H0 presumes that mu is 45, and yet a sample reveals an average of 50, then we will verify whether such an outcome, or even more extreme outcomes, are reasonable or not. In other words, the p-value is the probability that a sample result or more extreme values can occur when H0 is true. If the p-value is high, one would conclude there is nothing unusual about the result that has been revealed. There is seemingly no reason to reject H0 in that case. If the p-value is low, however, one could speculate that either the sample's random nature generated a result that is unusually far from what we had predicted, or that we simply wrongly assumed H0 to be true is the case or is the cause of this extreme result. When the p-value is lower or equal to the significance level, we will choose the latter of these possibilities. That is, we will reject H0. The p-value then becomes a measurement of the probability that our decision will result in a type 1 error. For example, the proportion of students at Marinopolis College that have failed more than one course has never exceeded 20%. A recent survey has shown that 49 students from a random sample of 200 have failed at least 2 courses before graduating. Use a hypothesis test at a significance level, 5%, to determine if the college will need to address the situation. The parameter of interest is the populational proportion, p, and the null hypothesis is that p is 20% or less, as we have mentioned that never more than 20% of students have failed more than one class. The alternative hypothesis would then have to be that p is greater than 20%. The sample result, 49 over 200, provides us with a p-hat, a sample proportion of 24.5%, which contradicts H0. However, is the sample result far enough from p equals 20% to be considered unusually far? Again, we have a one-sided test because to reject H0, only right extreme values for p-hat would be convincing. In this case, any number left of 0.2 would clearly lead to H0's non-rejection, but our result is in contradiction with H0. P-hat, in fact, is 24.5%. 4.5% to the right of 0.2. We will have to measure how likely results such as this one, or more extreme ones, are to occur, given that 0.2 is still a true value. In other words, we'll find the probability that a sample proportion will give a result that is 24.5% or greater, given that it comes from a population with a p of 0.2. Now remember from the central limit theorem that a sample proportion is always centered at p, and its standard deviation is root of p, 1 minus p over root of n. Until proven otherwise, we are assuming p is 0.2, and therefore p hat has a normal distribution centered at 0.2 with standard deviation of 2.83%. We're expecting the 70 most reliable sample proportions to be within 2.83% of 0.2, essentially. But remember, our goal is to calculate how likely the result our sample provided is of occurring. In this case, because of the direction of p hat, we'll have to think backwards and subtract from 100% the probability that p hat is less than 24.5. With the use of Excel, we will find 5.58%. Now remember, the p-value is then compared to the significance level. Since we had set this significance level at 5%, and our p-value exceeds 5%, we must conclude that the sample data fails to reject H0. We cannot conclude that H1 is true. Hence, there is insufficient evidence to conclude that the proportion of Marianopolis students who have failed 2 or more courses exceeds 20%. And it would be premature to put new student measures in place. Status quo is maintained. Remember that a p-value is a measure of risk. It's the risk of making a bad decision by rejecting H0. And in this case, the risk is over the level we had set at 5%. Here's an example which involves sample means, or a test on a populational mean. When Marianopolis College made the decision to move from the Atwater Pavilion to the Mother House, one of the main concerns was the impact that would have on average time of travel. It used to be 45 minutes to go to Atwater. If a study could show that the average time of travel had become less than 45 minutes, then this would provide great advertisement when doing high school visits. On the other hand, if the average travel time became more than 45, then Marianopolis would feel compelled to negotiate with STM to improve service to the college. Either way, a change from the current average time would require some measures be put in place. Use a hypothesis test at a significance level 5% to determine if the college will need to address the situation. The parameter of interest is the populational average, mu, and the null hypothesis, in this case, is mu equals 45. Its alternative hypothesis is to assume that mu is not 45. Actually, I shouldn't say assume. Our burden of proof will be to show that mu is in fact not 45. This is what we call a two-tailed test, as any deviation left or right from 45, that is, far enough, may lead to H0 being rejected. Now, suppose that the survey results from a sample of size 81 and a standard deviation 15 is to have a sample average of 50. 50 is in contradiction with what we expected, which was an average of 45. Now, is it far enough to conclude that H0 is a false statement? Now, keep in mind, 50 is to the right of 45, but that's not really relevant. It's the distance from 45 that is interesting to us, because a deviation left or right could still be as convincing. we are once again using a two-sided test where two different possible deviations could have rejected H0. Our sample result was to reveal a sample mean of 50, 5 units to the right of 45, a deviation of 5 to the left of 45, which is at 40, would have been equivalent in the sense that it's not equal to 45 and the same distance. So we will have to measure the probability of obtaining a sample mean of 50 and also of having a sample mean of 40 or less, as these regions are symmetric and are both representations of unequal values to 45. So in other words, our p-value will be the sum of these two regions, or by symmetry, we could just do 2 times the probability that x bar will be greater than 50, under the assumption that mu equals 45 is true. Once again, recall from the central limit theorem that sample means are normal distributions with mu as their center and sigma over root of n as their standard deviation. A conversion to z would give us a standard normal law, where z would represent x bar minus mu over sigma over root of n, which is the standard deviation associated to x bar. Until proven otherwise, we assume that mu is 45 and that that number is accurate. However, we have no clue about the true value of sigma. So a student t distribution will have to be used instead of a standard normal law. So notice how we have replaced sigma by s, and we have changed the name of the distribution from z to t. N minus 1 is what we call degrees of freedom, because the errors we are making on s depend on how big the sample is. The p-value that we are looking to find is then 2 times the probability that x bar will be greater or equal to 50. If we do our conversion to t, where we subtract mu and divide by s over root of n, then we will find that our p-value is 2 times the probability of a student distribution law being greater or equal to 3. It's with the use of Excel that you can find this probability by going into t_dist as a function, or in French, loi student. So the two areas that we calculated created a probability of 0.36%, which does not exceed the 5% significance level we had set. So there is statistical evidence that we should reject H0, and we can conclude that H1 is true. So in other words, our sample result was far enough from what we had predicted under H0 to be conclusive. In other words, we can conclude that the average time of travel will no longer be 45, and our sample states that it will be more. Negotiations with the STM should be put in place to improve the transit to the college. Status quo cannot be maintained. Although we have rejected H0 in our previous example, this decision is based on sample data that was potentially not representative of the true mean. The probability that our decision leads to a type 1 error is actually what the p-value measures and is equal to 0.36%. In other words, there is a 0.36% chance that rejecting H0 is an error. I think we can live with such a small risk of error.